and Mike will monitor. And I will introduce our next speaker and a truly new relatively new hire to U of T, and that's Rahul Krishnan. He is currently an assistant professor in computer science and medicine at U of T, and he's also a faculty member at the Vector Institute. He completed his PhD in electrical engineering and computer science in 2020 from MIT, working with David Sontag. And then he spent the next year as a senior researcher at Microsoft Research New England. So Rahul has been building machine learning algorithms to automate clinically meaningful problems and advance our understanding of human health. So he's here to tell us about that. And we welcome you to Vector. The floor is yours.
Thanks so much for the introduction, Graham. Can you hear me okay?
Sounds great to me.
All right, perfect. Hi, everyone. It's an honor to be here and tell you a bit about some of the recent work that we've been doing that's recently going to be published at AAAI 2022, happening in February. And so the topic of this talk that presents a little vignette of the kind of research that I do that lies at the intersection of machine learning and healthcare, and highlight some of the topics that my group works on, is about thinking hard about what constitutes a clinically meaningful problem, how can we tackle some of the challenges that exist in healthcare data, and how can we think to apply some of the modern advances in machine learning that have been developed in different communities of machine learning. And so today I'm going to tell you about SubLign, which is a deep generative model for clustering censored time series data. So just to kick us off, the outline of this talk will start with a bit of motivation. I'll then tell you a bit about some of the challenges that can arise when clustering longitudinal observational data, and why a naive approach to clustering data might not give you the results that you anticipate. And then I'll introduce SubLign, which is the model, and talk a little bit about some of the theory that motivated the design of the model. And finally, I'll talk to you about some of the experimental results that we have highlighting its utility for disease phenotyping on practical real-world data. So let's get started. So what really is the opportunity with electronic medical records? And Mike's talk in the last half hour perfectly set me up for this in the context of thinking about how do we build useful algorithms and useful software that can both improve our understanding of human health as well as improve clinical decision support. And so one of the basis that forms the recipes of a lot of the machine learning algorithms that have been deployed in healthcare today are electronic medical records. And if you look at a plot of adoption of electronic medical records over the last 2 decades, you'll see this pretty superlinear rise that's been happening and in North America and frankly around the world as well. And we can ask ourselves, well, what is this data really telling us? So this data includes everything from medical imaging, inpatient health monitoring, medical exams, patient-generated health data, as well as laboratory results. And so electronic medical records in many ways give us a view into the patient's underlying physiological state throughout their interactions with the healthcare system. And this view gives us an interesting opportunity to ask interesting questions about human health. And so specifically, it gives us an opportunity to understand diseases better. And so the topic that I'm going to focus at least on for this talk on is that of unsupervised learning via clustering. And so clustering is a problem that most of you will have a fair degree of familiarity with. And it's essentially the idea that we have a certain amount of data, and we believe that there exists heterogeneity in that data that we would like to uncover. And so the figure on the right talks about the underlying heterogeneity that's been discovered in the context of breast cancer, which is to say that not all breast cancer patients are the same. They exhibit variation in how the disease manifests, their response to treatment, and the eventual outcomes in both the short and the long term. And uncovering this kind of heterogeneity can dramatically improve our understanding of both the kinds of patients that come to the hospitals in the GTA or in Canada more generally, as well, if we have a big enough sample, of the disease in general. And so what we like to think about in this context of this problem is clustering patients who all suffer from a specific disease. And so this task of uncovering heterogeneity, it goes often by the name of disease phenotyping. And so it's well known that many diseases are biologically heterogeneous despite a common diagnosis. What does that mean? It means that when the doctor says you have asthma, what he or she really means is that you have the indications of one of many different kinds of asthma, which is to say the language in which we express how a patient is clinically manifested is not as subtle as how the patient actually manifests in the context of their comorbidities, in the context of the lab values that they have, as well as the context of the outcomes that they have, both in the short and the long term. And so a disease like asthma or autism can have a variety of complex phenotypes, and individuals could belong to one or more different subgroups of patients. And identifying these subgroups is important. For clinicians, it gives them an opportunity to think about how they can tailor treatments better. If they identify, for example, that subgroup 1 in the context of autism or subgroup 1 in the context of asthma respond to a certain medication better, then that's clinically insightful knowledge. And so new algorithms to identify this heterogeneity in clinical data are going to be really useful to improve our understanding of healthcare. So I painted to you two pictures. One was about the rising adoption of electronic medical records in hospitals around North America. And the second was about a problem, one of uncovering heterogeneity in data sets to learn and understand more about human diseases. And so the idea seems simple. We have data and we have a problem. Like, can we leverage observational electronic medical records to learn about disease subtypes? And so the answer is yes, but there's a certain set of challenges. And in particular, the challenge that I'd like to highlight for you today is that of censorship. And so one of the challenges that exists in observational data is the fact that not all patients have equitable access to treatment and care. And these disparities can rise because of access to care. For example, rural hospitals may close. Thankfully, in Canada, most of us have coverage for health insurance, but that's not true in a country like the United States of America. Different subgroups, for example, have varying degrees of trust in the healthcare system, and this in turn affects their access to care. There are disparities in treatment that are both known for different subgroups, and these vary across the kinds of conditions that patients have as well. And finally, we would have disparities in outcomes, for example, life expectancy by socioeconomic status, maternal morbidity and mortality by race, and so on. These challenges in observational data often manifest themselves as censorship. And censorship is essentially a technical term for missings, which is to say that you have data that is missing up to a certain point in time. And interval censoring is a specific kind of censoring that includes both left censoring, where data might be missing prior to an individual's visit to the hospital, or right censoring, where data might be missing after the individual has been discharged from the hospital because they choose not to go back to that hospital again. And so access to health insurance, geographic proximity to hospitals, and medical mistrust all contribute to the existence of interval censoring in data. So let's look at it with a simple example. Let's say that we have 5 patients in our entire data set, and we have the time series data corresponding to these 3 different biomarkers denoted in blue, orange, and green along a timeline from 2010 to 2021, where X denotes some amount of adverse events. This is an idealized picture of what healthcare data could look like. So in this picture, you'll notice that B and C seem to have very similar patient profiles if you were to look at their biomarkers over time, as well as their incidence of adverse events. But in reality, patients B and C may have differing access to healthcare institutions. And as a consequence of their differing access to healthcare institutions, we may observe varying amounts of data for patients B and C. That is, we may never observe the history for C, and consequently, if we were to naively try and cluster the time series associated with this data, we might mark patient C as being more similar to D. And so hopefully this cartoon gives you an idea of how censorship can effectively bias the results of clustering algorithms that exist in time series data sets. And so the key idea behind this work is really highlighting the fact that if you were to cluster the data while ignoring potential left censorship or ignoring this notion of alignment, then we would end up with erroneous clusters. So we have a couple of options here. The first option might be to manually realign the individual's patient trajectory. So we could ask a clinician, do you think these two patients are similar? They might notice the fact that they have disparities in access to care and override understanding from the data alone and say, yes, B and C are really similar because I think C just has a harder time accessing a healthcare institutions. But this process is expensive and it's time consuming for very large data set, and it doesn't allow us to scale well. And so in this work, we explored option 2, which is to think about incorporating alignment into a statistical model that is then used for clustering, and so the learning problem that we pose here is, can we effectively disentangle subtype identity from left censorship or alignment in time series data? And so when we're working with healthcare data, we might often have to set out a set of desiderata for what we would like our algorithm to work in, or the conditions we'd like our algorithm to work in. And so the desiderata for this kind of algorithm is that it should be able to work with irregularly sampled time series data. It should be capable of capturing nonlinear relationships that exist between cluster identity and the subtype of patterns. It should work when data is high dimensional, that is, we have more than a single biomarker that characterizes the underlying health status of a patient. And in this work, we develop a deep generative model that captures all of these desiderata. And so this deep generative model is called SubLign, which is short for subtype and alignment. And it's a deep generative model that jointly learns both patient subtype as well as the alignment time or the offset time that we suspect exists in that data. So this slide gives you an overview of the paper in general. So if you were to take one thing away from this 30 minutes, it should be this. The first is that we derive a noiseless model that is provably identifiable. So we provide an existence proof for the identification of the parameters of a noiseless statistical model. And then we generalize that model to make it much more practical to be applied to noisy real world data. And that's the slide in the middle, for which we develop a variational learning algorithm for parameter estimation. And it's a much more practical nonlinear model of time series data. And we apply this model to uncover subtypes both in 2 diseases, in the context of Parkinson's disease as well as heart failure. And so I'll highlight the results in heart failure towards the end of this talk. So let's dig deep into each of these parts separately. So as an aside, I'm not sure how many of you are familiar with the deep generative models, but I want to try to connect this model family to models that you have heard of in the past. So I don't have a lot of time to go into the background of deep generative models, but I will say that they're essentially latent factor models of high dimensional data. So if you look at the graphical model on the right, which is a graph that represents the structure of the model being posited, a latent factor model will say there is some low dimensional latent representation Z that, when transformed by a neural network whose parameters are given to us by theta, give us the high dimensional data that we observe. And so that's what I just mentioned to you, is what's known as the generative process, or the process by which a practitioner believes data was generated. But what's interesting about these models is not the generative process, but rather the inferential one, which is given a data point, what can you infer about the low dimensional manifold that generated this data set? And what's been shown is that this class of model families does a particularly good job at uncovering low dimensional manifolds from high dimensional data. And so what's shown to you in the middle is a visualization of the low dimensional manifold corresponding to a variational autoencoder, a very simple deep generative model that's trained on MNIST digits. And you'll see here that without any supervision whatsoever, it learns a 2-dimensional latent space for this 784-dimensional set of pixels, where class identity for digits is entirely segmented. And you'll notice that if I were to apply any naive clustering algorithm to this low-dimensional latent representation, then I get a really good classifier of class identity in MNIST, which is to say that these latent variable models in this family of nonlinear latent factor models seems to do a good job of identifying subtype particularly well. So that was just a quick aside about deep generative models, because this is a tool that we'll make use of in the development of SubLign. So remember, we're not working with pixels, we're working with time-varying patient data. And so the key point to keep in mind from the previous set of slides is that we need to correct for an additional term, this notion of alignment. And so in our work, we treat alignment as a latent variable. So to just to give you an example of what this looks like in practice, we can think of a disease for which there are two subtypes. The first subtype in blue has biomarkers increasing in this manner. And the second subtype for this disease in green has biomarkers increasing and then decreasing. And so what you see here are three different patients. And in reality, we never observe the shaded out observations in gray. But what we do observe are the observation and the data points in black. And so if we had a model that could shift patient A's data by up to this point in time and shift patient C's data up to this point in time, and if we were to cluster this data set after shifting their time series data, then effectively we would be able to uncover the subtype 1 in blue and uncover the subtype 2 as different regions in the latent space that we learn. So that's the high level idea that this model tries to get behind. And so once we would, after we correct for the alignment, we would like to learn this low dimensional representation of the time series data for patients that we have. And so the intuition here is that similar patients with different left censorship would still be close together, because in some sense, the post hoc correction of the left censorship would allow us to correctly identify where in latent space this patient's representation lies. And as a third step, once we have this representation for our entire set of patients in the hospital, we could then apply any clustering algorithm like k-means to identify which cluster they belong to. So that's really the three-step pipeline that this paper talks about. And I want to dig deep into the latent variable model that we developed here. And so the model here is quite simple. It's very similar to a conditional variational autoencoder or a conditional degenerative model. And for each patient, the data set that we have is a sequence comprising sets of timestamps and the associated biomarker values over time. So what we're going to do is we're going to learn a latent variable model of the biomarker values conditional on the observed timestamps. So we observe when we have a particular observation. Note that this observation time may not be accurate, but nonetheless, that is what we observe. We believe that there is some latent structure that characterizes heterogeneity in the biomarker values that is indicative of potential subtype for the patient. And we also note that there is some notion of a latent alignment associated with each patient, which is to say, this is their potential offset from when they should have come into the hospital. And so we assume that the low dimensional latent representation is drawn from a standard normal distribution whose parameters, whose values are then modified from or transformed from that two-dimensional latent representation onto the parameters of a polynomial function. And we model each biomarker by a polynomial of some degree p, which is a hyperparameter, and f is a nonlinear link function. So yi equals f of kappa of x plus delta I is essentially the application of a nonlinear function to the result of polynomial regression. And so we model the variation in time series biomarkers via a polynomial, which is represented by kappa. And note that the arguments to x, which is the arguments to the timestamp of each of the polynomial, are shifted by delta, which is the potential shift that is latent. We don't know it, we never observe it for a patient, but we believe we can infer it from their data. And so we explicitly correct for this difference between the observed time point and the actual time point for the patient. And the parameters of the model are learned via maximum likelihood estimation, and this is done via maximization of a lower bound, which I won't go into just for the sake of time. Now, you might think that there's many, many ways to pose the question of clustering time series data when you have high dimensional, potentially missing data under, like you do in observational health records. So why choose this choice? And so this choice was really motivated by our understanding of a much, much simpler noiseless model. And so a theoretical question that one can ask in the context of developing any new statistical model is, are there situations in which we can reliably disentangle subtype from alignment? Are there situations where we can know what the cluster identity or the latent representation of the patient is and disentangle it from the degree of alignment that the patient has given their data? And so the answer to this question is yes. And in the paper, we show that for a much simpler noiseless model, we can prove identifiability of a simpler variant of SubLign. And so I'll talk about the limitations of this noiseless case in the conclusions and discussions of future work. But it is comforting that there exists at least one model family in the big set of models that SubLign can represent that is identifiable. And so just for the sake of time, I'm going to skip past this, but it essentially highlights some of the three assumptions that we need in order to prove identification. Okay, so we have a model, we have a learning algorithm. How does it do on a variety of different tasks? And to answer this question, we simulated synthetic data from some known generative process with a pre-specified number of clusters. And we asked the question, how well do different algorithms for clustering time series data perform on this task? And so how well does SubLign recover cluster identity as well as the alignment time for each individual data point? And so SubLign is the model that's shown in bold. That is the model that I described to you in the past few slides. SubNoLign is a model that represents what happens when you take the deep generative models, but do not explicitly account for alignment time. And we see a discernible drop in ARI, which is the adjusted RAND index, which is the fraction of samples of pairs that have been assigned to the correct cluster assignment, whether it's the same one or the different one. And so a higher number represents that more pairs have been assigned to their correct assignment of clusters. And Sustain is another really popular algorithm for subtype and stage inference that was developed in the context of single cell data. And so what we see here is that across the board in the context of ARI, or the Pearson index, which calculates the quality of the clustering assignments that come about as a result of applying this model on synthetic data, we see an improvement in results. If we look at the swaps index, which is the number of swaps needed to sort the predicted disease time into true disease time, this is a marker of how well we recover the underlying alignment, which is unknown and latent in our model of time shifts for patients. And so here again, a lower number of swaps means that the model did a good enough job of finding the right alignment time for the patients in terms of their true disease stage. So the synthetic results give us some degree of confidence that this model family seems to do what we would expect it to do. And so we went ahead and tried it on a much, much larger data set of observational data now. And so this is real world observational data from a health system in the United States. We tackle the problem of trying to identify individuals who had been diagnosed with congestive heart failure. And so we took a cohort comprising about 1,500 patients who all suffered from heart failure based on the diagnosis at admission into the emergency room. The set of features were essentially extracted based on echocardiograms that were done to the patient. Apologies for the typo. And for each patient, we extracted a set of baseline features to validate the subtypes that were not used for learning the SubLign model and for clustering the patients. And so the one other thing I'll say about congestive heart failure is that clinically it's known that there are two kinds of heart failure, diastolic heart failure and systolic heart failure. And they have different clinical manifestations. And this was a good case study for this clustering algorithm because it was a scenario in which we knew what an expected ground truth could look like. And what we find is that when applying SubLign to this data with k is equal to 3, which is one more than the number of clusters we actually expect, we find that it accurately recovers that patients suffer from diastolic heart failure as well as systolic heart failure. So it recovers these known two clinical subtypes. And I don't show it here, but it's in the paper that if you were to try some of the other clustering algorithms that do not correct for left censorship, then you do not find that these features, note that these are not used in the clustering algorithm, but these are baseline features that are used for evaluating the quality of the clusters, do not show up as being significant, which is to say that we need to correct for this form of censorship in order to accurately identify these known clinical subtypes of heart failure. And so I noticed that we're exactly at time, so this is maybe a good spot to conclude. I want to say that this is one of an interesting example, I think, where deep generative models are a promising tool for pattern discovery and predictive problems in healthcare. But if we apply them just as they have been developed in contexts like computer vision or natural language processing, they may not work out of the box to the kinds of data that we have in healthcare. And we need to be cognizant of some of the observational biases and explicitly correct for them in the development of the model. And in doing so, we can recover known clinical insights. And perhaps, and this is ongoing work where we're applying it to data where we don't know what the true underlying number of clusters is, or we suspect there's heterogeneity in the clinical data, but clinicians don't know what that heterogeneity looks like. We can actually guarantee that we find new kinds of insights about diseases that we previously didn't know. And so I'll highlight here that there's two important limitations to this class of models. The first one is that the results on identification are currently within the scenario with noiseless observation. And so we're working on extending it to noisy observations. And this is a slightly more theoretical point, the theory with noisy polynomials gets very, very messy quickly. And so if anyone in the audience has an interest in thinking about problems along that line, please shoot me an email. And the second limitation here is that the model as it stands assumes that alignment and subtype are marginally independent. And in reality, we know this assumption is false because we know that individuals who exhibit more severe subtypes of disease are much more likely to show up at the hospital earlier than the ones who exhibit mild subtypes of the disease. And so this is a limitation that we're also working on fixing. And so with that, I'll conclude this talk, and I'm happy to take any questions that people have. Thank you for your time.
Great, thanks a lot, Rahul. So I think we're definitely open to having some questions, and please put your hand up or come on camera if you'd like to ask a question. And since I don't see a hand up, I'll start it just like last time, and I'm sure people will ask. Given that we had Mike Brudno give the first talk and Rahul give the second talk, I have a sort of a Mike and Rahul question, mainly for Rahul though. Do you think this model might be able to work for clustering unaligned genomic sequences?
Yeah, that's an interesting question. I think it should be able to work for clustering genomic sequences. The part that you have to modify is the decoder that transforms the latent variables onto the parameters of the polynomial. It's not clear to me that genetic expression data over time still, it makes sense to use a polynomial regression function for that. But I think if you were to modify that aspect of this model, the overarching framework should still be able to work and potentially correct for delays in perhaps when individuals were sequenced. Yeah.
Cool. Yeah, because I noticed the data that you use is kind of event based, right? And it happens at these specific moments in time, maybe a time stamped, and the genomic is much more dense. But there's nothing in the model that's sort of specific to it, the nature of it being event based, right?
No.
Cool. Okay. Does anybody have any other questions? Okay, I'm not hearing anything. Well, we're at 4:04, so it's fine. We can wrap up the Fields seminar. And thank you very much, Rahul. Thank you, Mike, for coming out and sharing your research with us. I think having these two health talks right now with everything that's going on in Ontario and the rest of the world are very timely. And I appreciate Mike's discussion too of efficiencies in the emergency room. So let's hope that this gets us out to some degree of the mess that we're currently in. So we do have a Fields talk in a couple weeks, and that's Andreas Kraus, connecting from the other side of the world. So definitely come out to that same time 2 weeks from now. So with that, everybody have a great couple weeks, and we'll see you all soon.
Thanks for hosting, Greg.
Thank you very much.